Today we're going to look at differentiation and specifically with polynomials. Now there's a central rule that we use when we're deriving polynomials, but part of what we need to do is understand the notation involved. And part of that comes down to understanding function notation, but then also being able to put that in the form of differential calculus. All right, so let's just start with the rule that we need to understand for differentiation of polynomials. So, for example, if I have a function of y equals ax to the n, our derivative is given by dy dx. That's the difference of y over the difference of x, which is really talking about the gradient of the tangent or the rate of change within the function. And the rule happens that we take n and we bring that to the front, we times that by a as a constant, x, and then we reduce the power of n. So for a quick example, if I had y equals 3x to the 5 plus 2x to the 4, dy dx here will equal 5 by 3 by x, and then we reduce the power of 5 by 1, that gives us 4, plus 4 by 2 x, and we reduce the power of 4 by 1, which gives us 3. And that gives us a value of 15x to the power of 4 plus 8x cubed. Okay. What you need to appreciate with this rule is that this rule can be expressed with, or in different ways, different notations. For example, you don't always have y equals ax to the n. Sometimes you can have fx equals ax to the n. And in this notation, we call our derivative, and we use this little apostrophe up here just to signify that this is saying derivative. Okay, and we say that that's a n okay, same thing, but you just need to be aware of the notation. Now, a couple of curious things with a couple of examples here is, for example, if I have 2x to the 7 plus 8x to the 3 plus 15x plus 27. Okay, there's a couple of items here, or a couple of values that aren't shown. And I'm just going to talk about each of it. First value that's commonly not shown is this 1. And the second value that's not shown is here we have 27x to the 0. So what happens here is when we're finding dy dx, and you must make this point, because this function or expression is expressed as y, we then must express the derivative function as dy equals, or dy on dx. And what we would do here is we would have 14x to the 6. I'm just doing the computations quickly. 3 times 8, 24, x squared, plus 15 times 1. So that's 15. And this would be written as x to the 0 because we reduced the power. Plus, if we think about here, this is 0 times 27, and we could reduce the power. We don't need to, but it could be written like so. Now, what we want to do is we want to evaluate these terms. So 14x to the 6 remains the same, 24x squared as is, but this x to the 0 is just 1, so that's 15 times by 1. And we can really just forget about it. We don't need to worry about it. And here we have plus 0 times 27. Anything times by 0 is 0. And again, we don't have to worry about that. So the idea is that we can simplify our expression as quickly as possible. Now, the other item which we want to consider is when we deal with a negative power. The same rule applies, but we need to be careful with how we do it. So, for example, I might have y equals 2x cubed plus 1 on x squared, like so. And I want to write this as a derivative function, or a derivative expression of the derivative. So I write it as dy dx because, again, it's been presented in y, and this is the difference of y over the difference of x, or we're deriving y with respect to x. And here I would have 6x cubed plus negative 2x to the negative 3. Now, I know that some of you may be asking, where did this expression come from? Well, it's come from here. If I expand this expression, I would write it as like so, 2x cubed plus x to the negative 2. And therefore, this negative 2 here has been brought out the front, which is shown here. And then I've reduced this power by 1, which is this negative 3. And that's how you would generally deal with negative powers. Now, you could also have an example, and I'll just do a quick one here, which has fx. Just want to change the notation up for you a little bit, and we might have 15 on x to the cubed. Well, I might rewrite this expression as 15x negative 3, and therefore my derivative, and note here that I have made sure that it shows as a derivative, okay? But this is going to equal negative 3 times 15, negative 45, x, reduce the power by 1, that brings that to negative 4, and I may rewrite the expression as negative 45 on x to the 4. It is always good with our expressions to make sure that we use positive powers, and that might mean that we have to represent them in a fractional sense. That's all today. Thank you.